Welcome to a world where tiny chips power big ideas. Today, we delve into the fascinating realm of semiconductors. These unassuming components are the lifeblood of our digital age, found in everything from our smartphones to our cars and even our kitchen appliances. They form the very foundation of modern technology, making our devices smarter, faster, and more efficient. But have you ever wondered how these microscopic marvels are made? Well, that's the journey we're about to embark on. So, ready to discover how these microscopic marvels are made? Buckle up! Semiconductors come in different flavors, each with its own unique properties. Some of the most commonly used materials are silicon, germanium, and gallium arsenide. Silicon, the star player, is favored due to its abundance and its ideal electrical properties. Germanium, though it possesses superior electron mobility, is less common due to its high cost and lower melting point. Gallium arsenide, on the other hand, shines in high-frequency applications and is often found in mobile devices and satellite communications. Despite the competition, silicon remains the material of choice for most semiconductor applications. The industry's familiarity with silicon and its well-established manufacturing process are hard to beat. Now that we have our silicon, it's time to turn this humble material into a powerful semiconductor. The journey from a silicon wafer to a functional chip is a complex one. Let's walk through it. Our journey starts with a technique called crystal growth, where high-purity monocrystalline silicon is produced. The silicon is then cut into thin slices or wafers, which are meticulously cleaned to ensure there are no contaminants. Next comes photolithography, a process that uses light to transfer a geometric pattern from a photomask to a light-sensitive chemical on the wafer. This pattern serves as a blueprint for the chip's circuits. After photolithography, the wafer undergoes etching, where unwanted material is removed to reveal the desired pattern. Deposition follows, adding thin layers of materials onto the wafer. The wafer then undergoes ion implantation, a process that alters its electrical properties by introducing impurities into the silicon. Lastly, annealing is performed to repair the damage caused by the ion implantation. But our chip isn't ready just yet. Let's dive deeper into some of these processes. Photolithography and etching, two critical steps in semiconductor manufacturing. Photolithography is akin to photography, where light is used to transfer geometric patterns onto a substrate. This process begins with the application of a photosensitive material known as photoresist onto the silicon wafer. A mask bearing the desired pattern is then aligned with the wafer. Exposure to intense light causes the photoresist to harden, leaving behind the intricate design of the mask. Now, we move to etching. Imagine it as sculpting on a microscopic level. The hardened photoresist serves as a protective layer, while the areas left exposed are subjected to etching. This can be done by either immersing the wafer in a chemical solution, known as wet etching, or by bombarding it with ions, referred to as dry etching. The end result is a silicon wafer etched with the desired pattern. With our patterns etched, it's time to add some layers. Adding layers and tweaking properties, that's where deposition and ion implantation come into play. Deposition, a key process in semiconductor fabrication, involves adding thin films to the semiconductor wafer. Techniques such as chemical vapor deposition, physical vapor deposition, and atomic layer deposition are employed to achieve this. Each process has its unique advantages, with the common goal of creating precise, uniform layers. But what about modifying the electrical properties of the semiconductor? That's where ion implantation steps in. It's a process where ions are accelerated under an electric field and implanted into the semiconductor material. This alters the distribution of dopants, effectively changing the semiconductor's electrical properties. Next, we have to heal the damage caused by ion implantation. Enter annealing. After the rough treatment, it's time for our semiconductor to recover. This recovery phase is known as annealing, a process where the semiconductor is heated and then slowly cooled. The heat causes the atoms in the semiconductor to vibrate, helping them to move into a more ideal arrangement. This process heals any defects or damage caused by earlier fabrication steps and adjusts the electrical properties of the material. But how do we know we've done a good job? It's time for testing. We put our semiconductor through a series of tests to ensure it's functioning as it should. These tests can check for electrical properties, structural integrity, and even how the semiconductor behaves under different conditions. Each test is designed to ensure the semiconductor will perform reliably when it's put to work in our devices. And voila, our semiconductor is ready to power the future.